Yeah, hello everyone. Okay, so if you have any query, so then you can start to ask. Just raise your hand and ask your question one by one. Am I audible? Hello. Hello. Am I audible? Can anyone reply?
Yes, sir, you're audible.
Okay. So now you can ask your doubts if you have any. So no query from Big Four. Okay. So I'm starting to summary for the Big Four. If you have any doubt in between, then you can ask. Okay. So first thing, so Big Four is started from the graph. So what is graph basically? So graph is a non-linear data structure, and it consists a set of vertices and set of edges. So we can represent the graph with capital G. Here, for example, we are representing graph by capital G, which is equal to the V comma E. Here capital V is the set of vertices and capital E represent the set of edge. So for example, here there is a one graph given in your screen. So how can we represent this graph in the set forms? So here G equal to V comma E, we can represent what is the vertices in this graph. So A, B, C, D, E, there are 5 vertices. So we can represent these vertices inside the set. And second is the edge. So we can represent the edge by, so here the name is assigned to every edge, E1, E2, E3, E4, and E5. So we can directly represent with the name if already assigned. Otherwise, we can represent the edge by the set of vertices. So which edge is connecting which vertices, we can represent this edge by using in the tuple, using the inside the round bracket a comma b. So here E1 is connected between a comma a and b. So we can represent this here inside the round bracket a comma b. So in undirected graph, we can represent in both way a comma b and b comma a. Both are represented to the one edge. So this is the representation of graph using the sets. So there are some different types of graphs we will use in the week 4 and week 5 contents. So here one is the example. So undirected and unweighted graph. So there is no direction given on the edge, and there is no weight assigned on the edge. So this first graph is called undirected and unweighted graph. Second is directed and unweighted graph. Here direction is given, but weight is not assigned for any edge. Sorry, we can see that this is the directed and unweighted graphs. So for directed graph, how we can represent these as? So if, for example, if you see the right graph, undirected and unweighted graph, so we can represent this a comma b as only by written as a comma b. We cannot written this as like a b comma a. because here edge is starting from A and finishing and reach to the B. So we can represent this edge only by A comma B for the directed graph. But in undirected graph, we can represent in any way, A comma B and B comma A as well. And third one is the undirected and weighted graph. So here there is no edge direction, but the weight are assigned on the edge. So we can call this undirected and weighted graph. And last one is the directed and weighted graph. So both are present. Direction is also present, and weighted are also assigned on the edge. Now,
Sorry to interrupt, sir. Good
yeah,
afternoon, sir.
good
Sir,
afternoon.
what do you mean by weighted graph?
Weighted graph, if some value or weight, some value are assigned on the edge. For example, if we are representing a graph for the map purpose, so if we are representing a road between the two cities, so we can assign a value just like a distance between two cities on the edge. So here
Okay.
that value is called the weight.
Okay, sir.
Yeah. So now question is the how we can represent the graph in Python and how we can use in our programs. So here, for example, there is one directed graph is given. How we can convert this graph into a Python data. So this graph representation is this g equal to v comma e. There is a set of vertices and there is a set of edges. So there are two types of representation. First called is adjacency matrix, and second called is adjacency list. So adjacency matrix we can create using a NumPy 2D array and nested list also. So we can create a adjacency matrix using NumPy 2D array and nested list, built-in list in Python. So here how we can represent this directed graph into a two-dimensional array. So this is the code. So here this is the set of vertices and this is the set of edge. Every edge here representing so every tuples inside the list is representing a one edge. So here 0, 1 is representing a edge from 0 to 1. Second edge 0 from 2. Third is edge from 1 to 3. So this is edge collection for the directed graph. For example, if we create this edge list for the undirected graph, so we have to represent in both ways, so 0, 1 and 1, 0 in our finite adjacency list or adjacency matrix. So currently we are just talking about the directed graph. So import NumPy as NumPy. So here we are creating a matrix using a NumPy. So all value initialized by the 0, and size we are taking from the length of the vertex. So how many vertex are there? So the total number of vertices are 5. So we will create a matrix 5 by 5 and assign the 0 value in all place. After that, we will traverse the edge list. For each edge I comma j in E, we will mark 1. If edge is present, then we will mark as 1. Otherwise, all remaining value are 0 if edge are not present. So after converting this process, we will get this type of matrix using NumPy. So here 1 is representing edge from row index to column index. Okay, so this is the representation using a NumPy 2D array. And second is if we use the nested list. So this is the Python list. Here we are just creating a Python list, amat equal to empty list. After that, we will just traverse the for I in range. Yeah, so we are creating a nested list here. So we will create inside the I for loop. For every value of I, we will create one row, and we will insert. So we are inserting a 0 in all place. We are creating a nested list of the size by 5 by 5. So there are 5 nested lists inside the list. So we are assigning all 0. After that we just assign mark as a 1 if edge is adjacent from I to j.
Sir, one doubt.
Yeah.
Sir, in for loop, for I in range size, so we will be taking the size of v list. Then the
Yeah.
size will be 5. So basically, 0 will not be counted. Only 1 to 4 will be counted in that size, right?
No. So range will be start from the 0, and size of this is 4, actually 5. Okay. So this for loop will be start for loop will start from 0 to 4. 0 to 4 index. So if you
Sir,
are writing
but
if you are writing here 5, okay, what is the
yes,
meaning is? Meaning is this loop will
it will
start from
start
the
from
0.
1 to 4, na?
No, it will start from the
0 to 4.
yeah.
Okay,
So
okay.
inside range,
Fine.
we are passing a single value, so every time a value will be start from the 0.
Sir, one more question. Can we use NumPy in portal ID?
I think NumPy portal is not supported due to some reason. Uh, because of that, we did not use any NumPy code inside. I think I remember that.
Okay,
So
sir.
I think adjacency list or adjacency matrix are created using a nested list for the assignments.
Okay, sir. Thank you.
Yeah. So here on what is this site? Yeah. So for in range size, we will create a row 1 by 1 and insert the column value 0 for in each row. And after that, we will append into the a mat list. And after creating a 0, all after creating a matrix, after creating a nested list, and after assigning a 0 in all place, so we will just mark 1 if there is an edge from I to j, we will mark as 1. So after creating this for this graph of for this given graph, above given graph, so our adjacency matrix like this using nested list. So here 0 1 1 1, so all 0 represent there is no edge from row index to column index, and 1 represent there is an edge from 0 row index to column index. So this is the representation of adjacency matrix using NumPy 2D array and adjacency using a Python list. Second representation is the adjacency list. Basically, we create this adjacency list using dictionary for the graph. So here the same vertex, same graph we are using. So size equal to len of p. Yeah. So we are initializing a empty list. And we will initialize for I in range size. Yeah. So we for every vertex we initialize a empty list inside the dictionary. After that, we just traverse the list I comma j in E and assign the destination value. For example, there is an edge. So yeah, this 0. So there is an edge from 0 to 1. So we will assign here a list 0 and append I. So we will append the 1 inside the list here. So for every node, we will create a adjacency list, and after creating, so this will look like that. So for 0, this is the initial this is the vertex where edge is starting. So where edge is starting from 0. So there are two edge on 0. So these edge are 0 to 1 and 0 to 2. And same for 1, there are two edges available from 1 to 3 and 1 to 4. The same for 2, so 2 to 4 and 2 to 3. There are two edges. Only one edge are available from 3 to 4. There is no edge from 4. So this list is empty. So this representation is called the adjacency list, where we are creating this by dictionary. Same for the undirected graph. Here actually, yeah. So actually here one edge represented by two combinations, so 0 to 1 and 1 to 0. So we have to add this value for both place. first for 0 to 1 and second for 1 to 0. We will mark as a 1. So creating number I comma j. Yes, so here I think so here we are creating an undirected edge. So these are the set of edges. So every 0 to 1 we are representing one type, but for undirected graph we can also represent that 1 comma 0. So we will add these 1 to 0 in these edge set. So every edge represented by two combinations, so 0 to 1 and 1 to 0. So we will create a undirected edge where this is the set E, and we will reverse all the combination and add into the edge list. So here by this loop we are adding a reverse combination inside in the edges list. So so same for the two-dimensional array, and again using nested list. So we are just creating one another set for undirected by reverse the direction of reverse the combination of edge, and same for the adjacency list. So here we are okay, so this is the same. Okay, so this is the first step to understand the graph, how we can represent the graph in Python. And so there are two ways, adjacency matrix, and there is another way, adjacency list. After understanding these topics, we can start to solve another problems. So first problem is graph traversing algorithms, or we can also say the graph search algorithms. So first algorithm is breadth first search. So how breadth first search is work? So I'm starting from 0. So you must remember that so we use just Q for the BFS and stack for the DFS. So in lectures I use a recursive way to solve the DFS algorithm. So but we can also solve this DFS using a stacks. So I included the code using a stack inside the slides. So here breadth first search, we are actually traversing the all nodes inside the graph. So this is the graph. So I'm using just a undirected graph. So same for the directed graph, this algorithm will work. So initially we are starting from the 0. We are applying this BFS on 0. So initially there is one Q, and there is one dictionary visited. Actually we are created two types of two data structures, Q and visited. Inside the visited we mark our vertex is visited or not, and we are using a Q for this traversing. So we are starting from the 0. This is the initialized condition for our algorithms. After that we will find the adjacent of 0, where we can move from the 0. So there is two way available. So we can move from 0 to 1 and 2. So we will, so what step is said? So we remove 0 from the queue and insert adjacent of 0 in queue if not visited. So we will remove 0 from the queue, and what are the adjacent which is not visited? So there is two adjacent, 1 and 2, and mark true in visited. So we already reached at 1 and 2 by the 0. So we will mark these 1 and 2 true in our visited list and insert the visited vertex into the queue. So 1 and 2 will be inserted into the queue. So in next step, which element, which vertex will be removed from the queue? First in first out way. So this one vertex will be removed. So we will remove the 1 from the queue and insert adjacent of 1 in queue if not visited. So what are the unvisited adjacent of 1 which are not?
3, 4.
3 and 4. So we have already removed 1, but we are inserting 3 and 4 inside the queue. So both one after when we remove one from the queue. So we have reached 3 and 4. So we will mark this 3 and 4 as a true. Okay. So now 3 and 4 is also visited. Now we will just remove 2. Now remove 2 from the queue and insert adjacent of 2. But now there is no vertex are available which are not visited. All vertex are visited. So this step will be skipped. Same for the 3. We will remove 3 from the queue, but still all adjacent of 3. So there are 3 adjacent of 3. So 2, 1, and 4. But all are visited. So there is no unvisited vertex are available. So this step is also skipped. After that, 4, we will remove the 4. So same for the 4. There are no remaining vertex are available, so which are not visited. So when the queue become empty, we just return the visited data structure by the algorithm. So this is the steps which algorithms work. So if you see the code, actually we are using one queue here. This is working as a queue. After that, we are just initialize. This is the initialization step. There is a one visited dictionary. We are initializing all visited so for all vertex we are initialized with the false value. We are creating a queue here. After that, we are so there is one source where we are starting BFS algorithms. So we are initialize that visited source equal to 2. After that, we are adding this v into the queue. After that, these are the steps until queue is not empty. We will perform these steps. Every time we will remove one vertex from the queue and mark all adjacent as it true. For k in a list j, so these will return adjacent vertex list. If not visited, then we will mark visited equal to true and append into the we will add into the queue if not visited. So after this process, we will get the result. So after completion of this process, we will return the visited dictionary. So this will be the output. If we are starting from 0, so all elements will be traversed. So so this is the BFS concept. So using this BFS, so there are some more concepts are given. BFS, so okay, so this is for BFS for adjacency list, and this code is for adjacency matrix. So only data structure is different. Here we are using matrix, and okay, this is the algorithm actually. Here we are using a matrix, adjacency matrix. Same concept we are using, which we have already discussed in the slides. But here we are calculating the adjacent. We are finding the adjacent using this neighbor functions. Okay, so in dictionary format in adjacency list, we can easily find in a one steps we can find out adjacent of any vertex. But in matrix form, we have to traverse all the columns for any row, any single row. So this is the neighbor function. It will return the all adjacent of any vertex. Here we are using this. So neighbor. So otherwise concepts are similar. Only data structure are different. Okay. So yeah, this is the list of paths from vertex B using BFS. Yeah. Okay, so yeah, this is some another version. This is another application. We can also say this is an application of BFS. Here we are using some BFS concept, and we are marking that only parent value. Where from when we reached at any node, so we will just mark that where from we are reaching. So for any given graph, yeah. So if we are talking about this graph, so we are starting from 0. When we reached at 1, so we will mark that the parent of 1 is 0. Okay. If when we reached at 2, so we will mark that parent of the 2 is 0. And when we reached at 4, then we will mark at the parent of 4 is 1. So there is only one step added in this code. So here actually we are maintaining a parent list. Yeah, this one. Otherwise, code are similar to previous one. So this is the visited. We have already seen that the previous code. There is only one added things is parent. So we are maintaining just a parent where from we are reaching from for on any vertex. Okay, so this is the single line which is modified in the previous code. Yeah. Next is the find level of vertex B using BFS. Yeah, this is a very useful code. I think it is related to one graded assignment, also, graded programming assignment, where I think we are finding the level of friendship, friendship level. We are asking the friendship level. So this is the basic for that problem. So actually we are managing the level numbers. So every time if we create, for example, if we have a graph, like that, we are starting from the aim. So this is the first level, 0 level, and after that the what are the next adjacent level is B and C. So this is the first level. After that we can traverse from B to F and E. So yeah, this is the F and this is the E. Okay, so so we cannot traverse from the C because the direction is in the reverse way. So after that we can traverse from the E. Yeah, this is D. So this is the level 2, this is level 3. Actually we are finding out this level things. So this level things also represent the shortest path. We can find the shortest path in undirected graph or directed graph using BFS. If weighted are not weights are not given on edge, so we can find the shortest path in terms of the number of edges. So here we can reach from A to D in traversing 3 edges. So this level is representing the shortest path also. We can reach from A to D in 3 edges. This is the shortest path. Okay, and we can reach from A to B in only 1 steps, only by traversing 1 edge. So this is label is representing the shortest path. So we can reach B and C only in 1 edge traversing. We can reach from A to F and E in only by traversing 2 edges. We can reach from A to D in traversing by 3 edges. So BFS is also used to calculate the shortest path in in the terms of number of edges in between. Okay, so this represents the number of labels where we are traversing using BFS. So next algorithm. I think a similar question we are asking in the graded programming 1. We are asking for the level of friendship. So you can use this algorithm to solve this problem here. Yeah. So same things. I think we are maintaining a parents things here. So you can just execute this code. I have created this summary documents. You just I will upload my website which I have created for the summary. You can execute this code and use according to your questions. So next problem is the DFS. What is the DFS and how we can perform the DFS on graph? So according to the name, depth first search. We will traverse the depth first, then after the second another depth. in the previous, the name is breadth first. We just traverse the all adjacent first, then after again next adjacent data. Yeah. So the concept of for the DFS here I explained using the stack. So in the previous BFS I explained with the cube, but here now the stack, I'm using the stack. So I'm starting from the vertex 0. I'm applying on the DFS from on 0. So this is the initialization condition. Initially we assign all the visited value as false for the each vertex, and we are inserting a 0 in we are pushing the 0 vertex into the stack. Yeah. The next step is pop 0 from stack. So we will pop one vertex from the stack. So and mark true. We will mark true. So here we mark true in visited and push adjacent of 0 in stack in if not visited. So what are the adjacent of 0 is 1 and 2. So both are not visited. We can check this in visited list. So 1 and 2 are false. So we will post these vertex into the stacks. So we can use any way. We can push smaller value first, or we can push large value first. So here I am pushing the smaller value first. So first we will push 1, then we will push okay, no. First I am pushing the 2 value, and then I'm second I pushing the 1 value. So here top is represent the top of stack, which element inserted in the last. So this top element will be removed first. So next step we will remove 1. We can remove only this top elements. So this is the first step from the now second step, pop 1. Pop 1 from stack and mark true in visited and push adjacent of 1. So what are the adjacent of 1? 3 and 4, which are not visited. So we will push these all vertex into the stack. So 2 have already inside the stacks. After that we will push 4, then we will push 3. Okay. So now next pop vertex will be 3. So next step, we will pop 3 from the stacks and mark true in visited and push adjacent of 3 in stack if not visited. So yeah, so there are 3 adjacent of 3 are available, 2, 1 and 4. But 2 and 1 yeah, I think, sorry.
Sir, in the stack, the sequence is not important, or we have to do.
Yeah, sequence is not important. We can add in any way.
Okay, sir.
Only just a traversing order will be become changed. Otherwise, there is no effect.
Sir, and repetition of numbers is also there.
Yeah, so repetition can be repetition will be there. Yeah. So here condition is that pop 3 from the stack and mark true in visited and push adjacent of 3 in stack if not visited. So adjacent of 3 yeah.
Sir, why are we pushing this 4 into the stack? Because if we are checking not visited condition, then it is false, right?
So yeah, so 4 is not visited, and so 2 is also not visited. I think skip some things. Yeah, okay. So here 1 is 2, 3, 4 I have added. Yeah, okay. So when I think I skipped some things. So when I am removing this pop from the stacks and mark true in visited and push adjacent of 3. So adjacent of 3 is 1, 4 and 2. Okay, so here 1 is traverse, so we will not check it, but 2 and 4. So 2 is also not visited. Okay, I missed it. So 2 will also insert inside the stack. Okay, I missed it. I will correct it. So those vertex are not visited. We will push into the stack. So there is no if vertex is already in stacks. Still, we will push.
So can you repeat this DFS a little, because get a little confused, sir.
Yeah, actually, one step I missed in the slides. Okay, I'm just taking an example on note. Okay. I'm created one diagram. So yeah, first initially, for example, if we are starting from A, okay, we will push in. So yeah, okay, step by step I create. So this is, for example, stack. So A will be pushed inside the stack, and for example, this is the visited list. So A, B, C, D, E. So initially, all will be false. When we remove element from the stacks, we will mark that vertex as a true. So we will remove first in step first. We will remove A. Okay. So we will mark here A value is true. F false, false, and false. But we will push all the elements which are adjacent of A and but not visited. So what are the adjacent of A? B and C. Okay. So B and C are, but both are not visited. So we will push into the stacks. So we can push in any order. Okay. So this is the top of element C. In next step, second step, we will remove C from the stacks. Okay. So this C will be removed, and we will mark this C vertex as true. T, F, A, B, C. Okay, T, F, and F. Okay, and what will be the updated stack? So B, we have already removed C, but what are the adjacent of C? B, B, and E. Okay, so B and E. Still, we have already in stack, but we will still push into the stack. B is not visited. Yeah, so B and next is E. Okay. Now third step is remove this E. Okay. So what will be the updated visited list? T, F, T. So this is the last. Okay. F, T. Okay. What will be the updated stack? So here now we have removed E. So B, there are two elements remaining B. And what are the adjacent of E? There is no adjacent. Okay.
No adjacent. Yeah.
Yeah. So so stack will be not updated at this step. And after that, one second. So we will remove B. Now in step 4, we will remove B, top of the stack. So now updated stack is, okay, I'm first writing this. So
Sir,
T,
D is the adjacent of B, na?
Yeah. So we will
yeah,
add
so
that now.
now we will add at this step.
Hmm.
So this is F, this is T. Oh, okay, sorry, we have more. Yeah. So B have already removed, so we will mark here B as a true. True. Or now this is F, or this is true. Okay. So what is the adjacent of B and D? So here B already is there, so D will post in this step. So now in fifth step, remove D. So we will mark T, 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 and T. but stack is not empty till now, so the updated stack, so there is no adjacent available now which is not visited, so only B is remaining. So in step 6 remove B. Okay, but it is already visited, already marked as true, so we will not update it. And so after that there is no adjacent available to add in stacks, so stack become empty in that case. So finally this is the visited list. When the stack become empty, we will return the visited list output. So this is the process to perform DFS using stack.
So here, because of this DFS sequence, a single element can remove from stack twice, thrice, right?
Yeah. So according to this algorithm, so we are inserting the vertex. If it is already exists, still we are inserting. So because of that, so I think it will not affect the answer. So we can skip only. I'm showing your code. Yeah. So this is the code where I perform the DFS using stack. This is the stack. Okay. And this is the DFS where I'm using the stack. So same. So here we are creating a stack and we are push one element, source element where we are starting from, and after that, while until stack is not empty, we will perform this. Every time we will remove one, we will pop one vertex from the stack and check that if visited of j equal to false, then we will perform the next step. If it is already true, then we will skip this part.
Sir, why are you reversing the A list like that? A node neighbors list?
This one.
Yeah.
Yeah, we can actually I'm performing just we are traversing small element first. Because of that, I just mentioned. If I remove this, the just order will become changed.
Yeah. Okay.
Okay, you can remove this one. Yeah. So in theoretical question, sometimes this type of question asked in the exam. So one graph is given. What is the order of what is the correct order of traversing Bfs and Dfs traversing? Okay, I'm just showing you. Okay, so if I'm performing the DFS on this graph, so what are the correct order? What are the possible correct order of the traversing? So we can just, for example, written that A, B, C, D, E. Is this correct order to traversing of this graph? So we can check that. So we can if we are performing DFS. So we will start from the A, then we can move to B. Yeah, that is correct. Then there is no edge to C now. Okay, so B to C there is no edge. So we cannot perform because in DFS we perform the depth first. So when we reach at the B, so we can traverse at the next level. So B we can traverse into the B to D, but we cannot traverse B to C directly. Okay, so this means this is the not possible order. This is the correct order of the traversing. Otherwise, if we write if A, B, D, then C, then E. So here, is it possible? Is it correct order of DFS? So
yes, sir.
Here we are traversing A to B, then B to D, then D to E, then D to C. So this is the correct order. Or we can also write that A, B, D, E, C.
No,
Okay.
sir.
Why no?
Sir, we can't go from E to C. No, we can go from C to E.
No.
We can go from A to C, right? So we will backtrack from
sorry,
E.
sorry. No, actually, we are starting from A. Okay, so we will move either B or either C. So here we are traversing B. So for example, we are moving like this way, A to B. After that, just check the next what is the next vertex, BD. So yes, we can move here. Okay. Now we D to E. So yes, we can move here. Now E to C. If E to C is not available, then we will revert back on the D. Okay. Then after revert back on the D, we will choose the another level. C. So order is correct.
Sir, so this path is not correct. Sir, how can it be correct?
This is the
After
order
A,
of
then we will
traversing. Actually,
return to D.
this is order of traversing.
Sir, so whatever the path, matlab, if a repetition of vertices is occurred, so we won't be mentioning that vertices again, vertex again.
No, actually, you cannot say this. This is path. Here we are traversing the element only. Actually, when we at the D level, okay, so we can push C and E on the stacks. But what are the order of the pushing the stacks? It can be changed. So we can push C first and then E. We can push E first, then C. So order can be changed. So because of that, these both traversing are correct.
Okay, sir. So in that, if D is occurred once again, so we will be not mentioning that.
If D, yeah. So in traversing, so we will not mention the D again. We are just marking the traversing. So if we create the, for example, if we create the tree for that, so okay. So here we are traversing A first, then we are performing B, then we are performing D, then we are performing E, then now C. This is the order of traversing. If we are creating the tree for this upper graph, so this is the tree. So after traversing E, we cannot directly move to C, but after revert back on D, then this is the another depth level. Same for the A, then B, then D, then C. We can write this like.
Sir, I think this is not possible practically.
Yeah, practically are not possible. Actually, we create a program in a specific, in a fixed way, but implementation can be changed.
Yes, sir. Exactly.
So, okay. So here I am writing this reverse order to inserting the push operation. So another way is if we are not following this, so the order will become different.
Yes, sir. I am saying we cannot, like, if we are choosing the descending order, then we will insert E first and C
Yes.
later, right? But if we
Yes.
start from A, then we have to insert C first, not B. So that is
Yeah.
not possible to get the.
It depends on totally. It depends on implementation. Our codes.
Yes.
What are the order of traversing actually? But both are correct. We cannot deny that this is not. If program is given, if the code is given, then there is one fixed answer. If code is not given, so both answer are possible. Okay. So only this is the incorrect way. A, B, C, D, E. This is not possible in any way. Okay. So after reaching at D,
Sir,
we cannot move to the C.
So third option is also not possible in both the ways, right? If we choose ascending order, then it is surely not possible. But if we are choosing descending order, then how is it possible? Like if we are choosing the main point A, then we have to traverse to C, right? Not B.
No, in theoretically, if we are calling theoretically, if I am moving to A to B, just not relate to any particular code. I'm just traversing theoretical way. So if I am traversing on one node on the next depth, so if I am moving A to B, then we can move from B to D also. Okay, this is correct. A to B, then B to D.
Yes, sir.
Okay.
So theoretically, it is possible.
After reaching at D, we can move any depth, either E or either C.
But
Sir, then
generally,
by
one convention we follow, na. So if I choose the ascending, entire traverse we will follow the ascending or
No.
descending.
Actually, if you find the DFS algorithm on the internet, so there are many variant are available. So you cannot fix this your DFS for any particular code.
Sir, then first statement will also be true, A, B, C, D, E, like from A
How?
to B, and we can't
Okay.
reach directly from B to C, then we will return to A and go to C.
No, but
Then
No,
D.
we have to reach
No.
the depth first.
depth, actually we are traversing according to the depth. So we can move A to B because edge are available. Okay. So we, after A traversing through, then we can reach at B. Okay, DB. But after B, we have to traverse D first. We cannot move to C. There is no directly edge available for the C. Just look from the B here. There
This
is
is
no
the-
edge available. So we will move to the next depth where we can move. So from B, we can move only on the next level of D. So this is the
Would it be
wrong
helpful?
way.
Sorry to interrupt. Would it be helpful if you could draw the tree diagrams for the both of these? Maybe
Okay.
it will help them.
Okay, so I'm just creating one other example. So for example, A. Okay, so for example, this graph is given, direction is also given. So in BFS, okay, I'm just creating the both tree. Okay, BFS and DFS. So if we are starting from the A, so what are the possible traversing? So A will traverse first. Okay.
B
So
or
after
C.
that, we can traverse B and C. So next order possible is B and C. Same for, we can traverse A, comma C, comma B. It is also correct for the next level. For I'm just talking about the BFS here. Order we can change. So just not relate to any particular code here. Just do it according to the concept. What we are actually performing the BFS. Actually, we are traversing the level first. So here first we traverse this A level, then we are traversing the next level, next adjacent level of A. So here the A adjacent is B and C. So we can traverse in B first, then C. We can traverse C first, then B. So both order are correct theoretically. Okay. So after that A, comma B, comma C. So after that B, we can move the next level. What is the next level after B? Is D and E. We can move in both. We can move on the both node D and E. But same thing, we can move. We can visit D first, then E. Either in A, comma B, comma C. Then we can choose E first and D. Both are same level. At the same level, we can traverse any node by the theoretical concept. Okay, so both order are correct. So now this order is also correct, this order is correct, and the both are next possibility are A, comma C, comma B, then D, comma E, then A, comma C, comma B, E, comma D. So all order are correct according to the BFS concept. But we cannot write order like that. A, after that D, then B, then C, and E. This order is not possible in BFS. So from A, we cannot traverse directly D, because the adjacent level is B, C, this B and C. So we can not traverse after A directly to D. This order is wrong. Okay, same for the DFS. So in DFS, if we are starting from the A, so we will traverse only any one depth. We can either move into the B or we can move A into the C. So A2 we can move B or we can move A to C. We can move any one depth. So both order are correct. After, if I'm moving to B, so we can move to C, D, and E. We can choose any one of them. So after then we can move C. It is correct. After A, comma B, C, then after moving at C, we can traverse C to D. Okay. Then D to E. So this is the one correct order. This is the one correct possible order. Otherwise, A, B, we can, after B, we can move this D. Then E.
And then C.
Yeah, this is also a possible correct order. But if I am writing like that way, A, just comma, E, B, C, and D. This is not correct because we cannot move directly to A to E according to the DFS condition. After visiting of A, we can move either B or either C. So both is correct, but we cannot move directly to A to E. There is no edge available direct from A to E. So this order is incorrect.
Sir, A, B, E, C, D is also correct, right?
Yeah, A, B, C, D, E. Okay.
No, sir, A, B, E, C, D.
A, B, E, C, D. Okay, A, then B, then E, correct. Okay, and then C, then D. Yeah, it is correct.
Okay, sir, thank you.
Okay, we are performing theoretically DFS and BFS, just not related to any particular code. If code is given, then perform, do according to the code. But code is not given, so perform only concept. What is the concept of BFS? Okay. So yeah, this stack version is given here. You can see this code from the summary documents on the side. Otherwise, sir, use this recursive way to perform this DFS. Here we are not using any external stacks, but we are performing this DFS using recursive. So recursion is also work as a stack internally. So after reaching at any node, we are performing DFS list again. So here we are recalling recursively. Okay, so okay, sites I have already mentioned. Just I'm written PDSA. So currently till B3 I have uploaded. I'm just sending chat box. Yeah. Okay, sorry. Yeah. So here we are calling recursively this DFS here. When we reached at any node, for example, if we are performing DFS at node A, then we will move to the adjacent of A, B, then we will perform the DFS same node. So we will check this DFS will check again the next adjacent of B, where we can move. So after, for example, we are moving from B to D, then we will call again DFS on this node. So in this recursive way, we can also perform the DFS. Concept is same, but the implementation is different only. So yes, so some this is here actually we are passing a visited and parent node inside the function. Second versions are explained with using globally this visited and parent. We are using this dictionary. We are using this dictionary globally. So otherwise code is the same. So this is the code for adjacency list. This is the code for adjacency matrix. So same like here we will use the neighbor function to find the adjacent of the any vertex. Global. Yeah. So all codes are approximate. Yeah. So The next is application of Bfs and Dfs. So first application is find component using Bfs. We are just find the how many components are available. Basically, we can say that how many disconnected graphs are available. So for this example, so there are two components. The first component, these all vertices are connected. So 3, 4, 5, 6, 7, 8, 9, and another second component is 1, 0, 2. So I think one graded problem is based on that. Yeah, I saw yesterday session. So somebody says that the problem are very difficult in Big 4. So actually every problem are based on any one particular algorithm. So if I'm saying that GRP1, so this is the BFS level. This is based on the BFS level, connection level. Second, find master tank. Okay, this is also based on the BFS. We just check that we will apply the BFS algorithm on every node one by one and just check that all nodes are reachable from any particular nodes. Just apply that BFS on each node, each vertex. For example, here, if you apply the BFS algorithm this one node, check that all vertex are visited or not. If all are visited, then all are reachable from one. So if we can say that this is the master, we can say that this is the master tank. So just apply the BFS algorithm on each node one by one and check that all other nodes are reachable from them or not. So this is also related to BFS, and third one is related to the longest path of perform on the DAG. So if you just see this code, so this is based on the last topics which covered in the lecture.
So can you also tell about PPA3?
Yeah, sir, please.
Yes.
About PPD.
Actually, PPA3 is just competition-based problem. Okay. This time I'm feeling that the PPA's problem are difficult compared to
comparative to GRPs.
Yeah. First problem is very easy. Here we are performing just finding the components. Yeah. So okay, I'm just giving the hint. Actually, here we will perform the BFS algorithm.
Sir, first of all, how can we represent, like, which data structure we should use in this problem?
Actually, we will create a adjacency list using this input, cross and star. This input, because here we are giving this input in the same way, cross, space and star in the same way. So scan line by line. First perform the reading line by line. We will read the all line. After that, you have to create a vertex. You have to create adjacency list for each line, for each position. Actually, you have to create a vertex. For example, this is the first vertex, first X. So what is the position of this? This is the line number 1 and column number.
So you are saying if there is any way, like if there is any space, then only we will append the element to the adjacent list, right?
Yes. So if there is any space, so what are the possibility of from move to available? So we can say that the 2, 0. If we are starting from the column 0 and column is 2, so 2, 0. So we can move 2, 2 position. We can move. Yeah, there is one position we can move from 2, 0.
2, 1. Yeah.
1. Yes. So we will create the adjacency list and create the edge according to the where we can move. First, we have to create the adjacency list from this input. After creating the adjacency list, just find the label, find the total number of labels to reach from is 2 to 0 to this star position. The star position, we can say that 9, so 0, 1 to, oh, there are lots of approx 9 to 8 or 10.
So we have to build like a edge list and that
Okay, this
convert
is
that
PPA.
into.
Okay, I'm just showing the code to you. Okay, just
Sir, don't
Yes,
show it.
chap, please don't show the code. Just
okay,
give us
okay,
the
no,
hint.
no. Yeah. So hint is already if just read the each line one by one. After that, create the adjacency list when you can move from any one point to another point. So you have to choose the vertex from column level and row level according to. You can create a node like in that way. The position level. So if the for example the first x we can represent it by 0, 0. Okay. In the down second where this is the empty place, so we can represent it that 1, 0 starting position.
Sir, actually what you're saying I was able to do with DFS, but it's taking so much time that it's giving me a runtime error. Like DFS is checking every possibility in the whole graph.
No, actually you
So,
can
sir, so the keys of the adjacency list will be the spaces and the neighbors will be the element in the list, right?
yeah. For example, we can represent that. For example, this is the first. Sorry, this is cross like that, and next is the here from here. Okay. If we read this list, for example, if I'm creating the, we are scan the all line by line, we can create a list. So every list inside there's a one x x x x x x. Second list will be like x, comma space, comma x, comma x. Oh, there is one here also. Okay. So sorry, this is the now first list is x x x comma. So 1 2 3 4 4 5 6 7 1 2 3 4 5 6 7. Okay. Next is first is empty and second is x. 1 2 3 4 5. X x x. So 1 2, there are 2 comma here. Okay, this is first space, second space, and this comma for the second line. Same for the third. So x comma space x x x. We can create a list like that. After that, we will just create an adjacency list. So where when we find the empty locations, so we can represent this location like that. So we will create a adjacency list dictionary using dictionary. So we will just give the position. So what is the position for this empty space? So this position is 1 1, 0. So initialize dictionary like that. Where we can move from this position 1, 1. Okay, so we will initialize dictionary like that.
Okay, sir. Now what?
Okay.
Yeah.
When you reached at this place, for example, this position is A11. Okay, 1, 1. Where you can move from this location, you can move backward. You can move either 0, 1, sorry, 1, 0, or you can
1,
move
1, 2.
2, 1.
So yeah, 2, 1, yes.
1. Okay, so you can create the adjacency list in that way. After creating adjacency list, just find out the label and what are the position of this star which is given in the problem.
And it will represent undirected graph, right?
Yeah, it will represent the undirected graph. Undirected. No, not undirected, directed graph. Okay, we are here. We are representing that we can move from 1, 1 to 1, 0 or 2, 1. And when we will 1, yeah, if it is empty, yes, it will become a undirected graph.
So those X's are like redundant information. We are just removing them while creating the A list.
Yeah, the spaces are important here.
Yeah, spaces are important. So just apply the BFS at this from this position, or this is the actually destination position. Just find the label of, after apply the BFS list path algorithm on this node, just check the what is the label of this star. After that, apply the algorithm BFS list path from here, and then check the exist position. What are the label of this that exist location, and add both label value. So that will be
Exit
the
location will be on last column. Like that.
yeah. So it depends on the inputs. Where is the exist location? You have to find out that after reading the inputs. Where is the exist location?
Okay, sir.
So this is the actually this is completion list question. So try to solve. Otherwise, graded problem are very simple, directly based on the 3 algorithms, or just the lectures algorithms. Okay. So components using BFS, we can find out the how many components are available. So algorithm are very easy to. We are using the Q algorithm, Q structure for this. Same. This is the we are using the BFS list. After that, we are finding out the components. So we will start from any one particular node, or we can start from any node, and just check that how many after traversing using BFS, how many nodes are visited. If all nodes are not visited, then we will start from the node which is not visited. So every time we will increase this path label, or we can use a component label by 1. So we can represent graphically like that. What we are doing, if graph is for example like a like that. So there are total 6 vertex in the graph. We will start, for example, we will perform the BFS algorithm from A. So after when we will apply the, initially we mark that false for all node A, B, C, D, E, and F. So all node we will mark as false. Okay, we will start from any node. So we will, after we will apply the BFS algorithm on A, we will just we can how many nodes we can reach from A. So B, C, D we can reach. So after performing the BFS on A, so these become true. Okay, then we will check again that how many how many vertex are available which are not traversed. So there are 2 vertex E and F are not visited. So we will apply the algorithm from here. So for these vertex which are visited on the first step, so this is called the component 1, and this after second time we will apply the BFS algorithm on that. So mark as true, then true. This is as the second component. This will become the second component. So actually we are just finding out how many components are available in disconnected graph. If all nodes are connected, so there is only one component will be there. So we are performing.
Is this the best way to find components?
Sorry, is this best way?
Best way to find components.
Yeah, I think this is, or you can also perform the DFS. So same like a DFS. The DFS is also a traversing algorithm. So,
Like, are there any more efficient algorithms, or like only BFS or DFS can be used?
So for finding components, I think this is the correct. Otherwise, if you have any solution for this,
Sir, is there any other reachability algorithm? Like, then only we can find the components, right?
So reachability algorithm, actually we will learn some algorithms in the next weeks where some shortest path algorithms are given. So here we are also find out the shortest path. So I think this is not sufficient. Shortest path algorithm will not good for them. Bfs and Dfs is I think efficient. I didn't know any another approach. So this is, I think, efficient algorithm. If you have any another solution for the graph reachability, maybe some advanced algorithms are there, but currently this is the basics of the reachability. Same for the next one applications are discussed pre-post using DFS. So here we are marking we are increasing the pre value when we reached any vertex, and when we left any vertex, it just increase the value of post. So by using this recursive algorithm, so we can perform this pre-post traversing. So for example, if we are starting from the 0, and we can move, so the pre-value of the 0 is 1, then we will move to the 1. So the pre-value 1 become a, sorry, we are starting from the 0. Okay, so 0 for 1, the pre-value become a 1, but after that we have to reverse back to the 0. So we are after traversing, we are lefting the 1, so we will increase the post value here. So post value become 2, then we will move to the 4. So pre-value become 4, then we will move to the 8 or 9. So every time when we are entering any vertex, so we are increasing the pre-value, and we are lefting from any vertex, so we are increasing the post value here. So this problem, the graph solution is there. So you can just check, compile this. After we are here, you can see the solution for this graph. So here we are starting from this line is representing the pre-value, this representing the post value. So you can see that the 0, then 1 become pre-value 1, then after that we are leaving the 1, so post value become 2 for the 1. Then we are entering to the 4, so 3, now pre-value for 4, then for 8, then 9. After that we are returning it back, so we will from the 9, so 6 become a post value for 9, 7 become a post value for 8, then 8 become a post value for 4, then 0 become 9 become a post value for 0. So this is the pre-post example.
Sir, back edges is used to detect cycles. So then what is the use of like forward edges? Like
yeah, using BFS we can track that graph is cyclic or acyclic. We can detect a cycle inside the graph. So back edge, you can use DFS algorithm to detect the cycle.
Yeah, using back edges, right?
Yes.
So then what is the use of forward edges? Is there any?
No, forward edge is actually when we are creating the tree from the graph using DFS. So if cycle is not present, so we can use these forwarded edges. So backward edges is not part of the tree actually, because we not consider the backward edge. Because if we are moving from 0 to 1, then it become a node in the tree, but we will not mark that 1 to 0 again. This is the backward edge, so this will not part of the tree because it is creating a cycle. Or same concept we can use in the detect. Sometimes problem is given that check that graph is cyclic or not, so we can apply these algorithms. Yeah, next is the directed acyclic graph DAG. So what is the directed? If graph, so in directed acyclic graph, there is no cycle should be present in the graph, and that is, it consists of vertices and edge. with each edge direct from one vertex to another, such that following those directions will never form a closed loop. Yeah, so there is in DAG, there will not be cycle should not be present, and some vertex are available with in degree 0. These are some conditions for the DAG. First is cycle should not be present or closed loop should not be present, and second is some vertex should be available with in degree 0. After that, we can perform some application like topological sorting and longest path. So topological sorting, there is one example. Yeah, this one. So we are maintaining a two dictionary here. So one is in degree and second toposort. So initially we are calculate the in degree for each vertex. So here first in degree list contain the in degree of all vertex. So 0 and 1, there are two nodes available with the in degree 0. We can start from any node. So here we are starting from 0. We can start from any node whose in degree is 0. Here we are starting from 0 and removing vertex 0. So after removing vertex, so this edge will also remove. So there are three edges related to the 0 will remove. So yeah, so topo sort list first we have choose the 0. After removing 0, so 3 edges removed. So all we will update the in degree of all vertex which are related to the direct edge from 0. So after removing this 0 vertex, so we have updated the edge. Now there are three nodes are available with in degree 0. So 1 and 3 and 4. We can select anyone. We marked in degree -1, which we have removed from the last step. So in the next step, we have select 1. Okay, so next selected element is 1. So we will mark at the 1. And after removing 1, we will update the in degree. So every time after removing the vertex, we are updating the in degree of each related vertex. So now there are 3 nodes available, 2, 3, 4. We can select anyone, but here we are selecting the minimum value. So we will select the 2. So same for the 2. After removing this, all degree will be updated. So 3 and 4, 0 now. Now after removing 3, so 4 and 5 become 0. We can select 4. Then after removing 4, so 5 becomes 0. Then after removing 5, 6 becomes 0. And then after removing 7. So this is the process to perform toposort on the tag. So this is the way to perform toposort according to the algorithm. So here we are maintaining this algorithm in degree. Initially we are initialized with 0. After that we are calculating the in degree for all vertex. Then after that we are managing this removing process. Every time we select the minimum in degree node, and if in degree k equal to 0, this line. Yeah, and add this removing vertex into toposort and reduce the in degree by minus by 1. So this is the step for toposort. And this toposort using the adjacency list. Upper is using adjacency matrix. So concept are same. And next is the longest path in DAG. So what is the longest path concept actually? So here we are maintaining a 3 data structure in degree, L path, and 0 degree Q. Basically, we are using Q. So in every steps, so if we are starting from the 0, we can start from any node. So we can start from 0 and we can start from 1 because both have 0 in degree. So for the longest path, we maintain a queue. We will insert the vertex which have in degree 0. So initially 0 and 1 we will insert into the queue because both have the in degree 0. Then select the 0 node and remove from the queue. Actually, here one logic is there to update the L path. Okay, actually we are increasing according to this formula, updating max one. Or in simple way, we can just update the label. Sorry, L path, yeah, 3. Okay, we can understand this easy way. I draw this down.
So can we use BFS also for longest path?
No, BFS used for the shortest path.
So if we'll use the count level as -1 and the maximum negative weightage of the edges, we will get the longest path.
No, I think for longest path, actually BFS traverse the nodes by label. So how you can maintain the longest path value? The graph. You can just you can try with your logic which you are thinking that, and just check that answer are correct. Otherwise, BFS used for the shortest path in terms of the number of edges.
Okay.
Is there any cycle available? Okay, no cycle available. Okay, so if we are starting from the integer 0, so this is the selected first vertex selected, which have the integrity. It is also in degree 0. Okay, so we just mark that one condition. Okay, so we can remove only first at this step. So we can remove only this step 0. So yeah, this is the first. After removing this, so initially what are the integrity for this C? So here integrity is 1, here 3, here 2, here 1, here 2. Yeah. So initially all the integrity are this. So we will remove the degree which we will remove the vertex which have the degree 0. So initially this is the first node only which have the in degree 0. We will remove this. After removing this, so the first removing node is A. After removing this, so this vertex will be removed. So in degree becomes 0 for that C, and this for 2 become 2. Okay, so in next level we can remove only this C node. So next is the C. So after removing C, it become this become cross. Yeah, so it become 1 and it become 1. Okay. Okay, so I think there's no node of graph is not connected to this. Okay, graph is not connected because after that there is no.
This graph is cycle, sir.
Where is? Oh, okay. Sorry, missed it. Yes. We can. How can we remove this cycle? If we connect this like that. Yeah. So, for example, after removing, so this is the correct. Okay. So after removing C, this now E become 0. Yeah. Okay. So next place will be selected as E. So yeah. So after removing this, it becomes 0. Become 0. And yeah, this will become 1. Yeah. So in next level, we can remove 2 nodes. So first is D and second is B, because both have the 0 degree. So D and B and D. Okay. So after that, F. So the longest path is this is the minus. So where we are starting from actually. Yeah, we are starting from 0. Okay. So yeah, this is 0 value. This is the 1. This is 2. This is 3. This is 4. Yeah. This is the value of longest path for each node. After completing the process of this stack, actually. So for this graph, if we are performing this deck concept, so after completion of, actually there is an algorithm given. So after removing that, this L path will be updated. So every time, actually, if this graph is given in the journal form, so how you can solve without any program, how you can solve manually, just removing the node which have in degree 0. You can remove both. You can remove many nodes at the same time. If 2 nodes are available with in degree 0, you can remove at the same time. So in that way.
Sir, is there any way by which we can keep track of the nodes that will come under the longest path?
Oh, actually, you are asking the solution for the GRP3. So GRP3, actually, I know that it is related to this longest path problem. You can maintain yeah, you can maintain a parent's dictionary, and after reaching at the final vertex, you can just traverse in backtracking way.
If we know the first and the last node, we can backtrack the.
Yeah, you can backtrack the. Just check the last destination node. What is the parent of destination node?
Like we did in BFS, right?
We can find the last end with the topological longest path, and after that we can use that.
Maintaining a parent-child dictionary.
Okay. Yeah, so you have to maintain a parent's dictionary for each node. Therefrom, you are reaching from any node.
Okay, sir. Thank you.
Okay. After that, you can just use the backtracking concept, back traversing, and find out the way. So yeah, these are the concept for Beak 4. So okay. So is there any query? Another query? So I have collected all the codes from the Beak 4 and put into these notes with examples. I will upload this summary by today evening or maybe tomorrow. You can directly run from the area. Just copy the code and directly run from there. Okay. So is there any query regarding any topic?
So this Friday, will you release the week 5 content, or the next week is a revision week?
No, actually we will release the week 5 content. We will release the week 5 content on Friday, and maybe your deadline will be increased for this week 5.
And sir, when will you release the mock for quiz 1?
I think so. Revision session for the quiz 1 will happen on the Thursday. Okay, for the same day today, like today, we will perform the. So there is no live coding for the live coding session for week 5 before the quiz. We will perform the live session in next after the quiz. We will, I think, for mock exam we will release on Wednesday or Tuesday. We will release.
So how many mocks this quiz? 25 or 50?
Mock?
Marks.
Marks, sir.
So you are asking about the questions? How many number of questions?
Quiz 1 will happen for 25 marks or 50 marks?
50
So,
marks.
numbers of questions will also help. How many number of questions do we get?
For
The
quiz
exam?
one, I think approx 15 or 16% approx. In
16
45
questions.
Yeah.
The mock you are going to release, sir, will that be timed or normal?
No, actually, we will release on portal. You can just similar to your like assignment things, but there is no deadline for it. You can just like a practice assignment. You can just check the answer after solving this question.
Sir, the slide which you shared right now teaching week 4, the summary part. So after graded submission of graded assignment, you will release that in
No,
that
no, no. I will
GitHub
release.
portal.
I will release maybe today or maybe tomorrow.
Okay, sir. Thank you.
Okay. I think you know the sites.
Yes,
Yeah.
yes. In the chat box you have posted.
Yes, yes, yes. Or the content in the theory paper is most of the part of the concept based, not the code based. Code based question are less, and concept based question are.
Sir, one more thing. Sir, on 29th of Jan, the revision session of quiz 1 is going to take place. Can it be reshifted to 28th or 27th? Because
No, no,
just
no. Actually, the revision session will be happen on the Thursday session,
Thursday. Okay.
not the Saturday.
Okay, sir. And sir, when
Actually,
will be the mock?
you can check the calendar. We have already updated the
Okay,
calendars.
sir. Okay, sir. Yeah, yeah. And sir, when will be the mock will be released?
Before the revision session, we will release the mock.
Okay, sir. Fine.
But
Thank
this
you.
time, PDSA we will release only one mock. Okay, for the quiz one. After that, we will not release
Okay.
any mock because the all exam in the similar way.
Okay, sir. Fine.
Okay, so just to learn all the concept clearly. What are the concept actually in the sorting, graphs? The mostly question are based on the concepts. Any other query?
No, sir. Thank you.
So I have a doubt. In the quiz, when we'll be going at the center, would we know the time limit is over for our slot? Like, for example, if a person has 3 exams, he or she will get 3 hours. But will they know that 3 hours have passed? After 3 hours have passed, I mean, because the exams is 4 hours long, and I heard like rumors that maybe the exam was 4 hours, so marks were deducted because of something like that. I don't know the entire issue. But would a timer be given for 3 hours, 1 hour after each hour, so that we know that time has passed?
This issue was solved last time, Karima.
Depends
don't
on
know.
number of subjects. If you have 2 subjects, then 90 minutes. The timer will be of 90 minutes.
Okay,
Yeah.
okay.
Exam is in the combined form.
I didn't know. I'm sorry. I was just asking.
I think
If you-
Okay,
every
cool.
subject you have a 45 minutes.
yeah,
Yes, sir.
Yes, sir.
number of
You can
subjects equal to
you can
number of
reduce
time.
your time for any one subject, and you can use your time in another subject.
Okay, thank you, everyone. Thank you, sir.
Sir, all this graph problem where we use stack or queue, do we need to have a linked list type of formation, or we don't need?
No, not for graph problem. There is actually we are not creating a graph in any problems. Actually, we are solving the graphs problems, or not creating a graph. So there is no formation like a link using the linked list. But in tree, maybe you have to use to creation of a tree to solve the problem, some problems. So graph can be represented in adjacency matrix and adjacency list. So after that you can solve by use of it. But in tree, I think some problems are Hoffman codings where you have to create a tree. So you have to maintain a linked list concept when you create the tree.
When it is coming in week 5 or later?
Tree things will come on the week 6. So in next week 5, so two topics are there: shortest path algorithms and spanning tree algorithms. So week 5 problems will be light compared to the week 4.
So there is any trick to find the time complexity by like
Showing the
seeing
code.
any code? Yes, sir. That how much it
just
will take
you
time.
Just you can start from the what is your inputs and what are the lengths of your input. Just check that what are the inputs for your code, and second just check that what are the how many loops are there. Just check that, and your loops are depending on your inputs or not. So I think by looking the loops you can easily find out the complexity in general way. Otherwise some recursive. So I've already saw some. Okay, so I'm explaining that. This PDS. So here some codes are given. So by this, can you tell me the complexity of this code?
So order 1.
Order
Big
1,
of
because
1.
here if for any input of A and B, so these 4 steps will be executed every time. So the total number of steps are not depending on the inputs. Every time these 4 steps will be executed. So the execution of the steps are constant. So we can retain as the big O1 complexity, constant complexity for that. In the second program, actually, if we are providing this n value, so the number of execution of steps will be depend on this n value. If we are passing n equal to 10, so this for line number 2 will be executed and approx n times, and same for the 3. Line number 3 also will be executed 10 times. And if we are providing this n value equal to 100, so this number of steps will be executed 100 times. So here we can say that this for loop is depend on the inputs n. So we can represent that the complexity of this code is big O n. So by looking the code, you can just check that how loops are using in your code, and loops, how loops is depend your input or not. So here is for the second. So we are using first loop. Inside first loop, for every value of first loop, we are performing second loop for n times. So we can say that this line number 4 will be executed n into n times. Okay, it depends on the n.
So when the J part, the second loop, if we are using the loop for I to n, like I plus 1 to n, then also it is for n square, or?
Yeah. So if you are using, for example, you are performing first loop is I 0 to n minus 1.
0
okay?
to n, yes. Yeah,
okay.
0 to n
In
minus
the
1.
second loop, you are performing I to n.
I plus 1, yeah, I plus 1 to n.
I plus 1. Okay, so at this case, one sequence will generate. So initially, first case, you are performing actually n step in the first case. Okay, for I equal to 0, you are performing
0.
n step. I
Yes,
equal
sir.
to 1, you are performing n minus 1 step. 2, n minus
n
2
minus
step.
2, n
like
minus
that,
3, 2, 1, yeah.
Dot, last 1. So this is this become a series. So sum of this series actually is n into n plus 1 by 2. Okay, when you solve this series, so n square by 2 plus n by 2. Okay, so the highest order of this solution is big order of
Big O of n square.
Yeah, n square. So
Okay.
you can write the complexity n square.
Okay.
Okay. So you can calculate the complexity. Same for this code. Here we are performing 3 nested loops. So what is the complexity? So big O n q. But when we use the combinations, for example, you are performing some operation sequentially. After completion of one loop, you are starting the second loop. So for example, this is the combination of all previous codes. So this part is, what is the complexity of this part? Big O n. What is the complexity of this part? Big O n square. Okay. And what is the complexity of this part? Big O
Big
n
O of
cube.
n cube.
But both operations are performing sequentially. After finishing of one operation, we are starting the second operation. So in that case, we will pick the highest order of the complexity in your code. So this part have the highest order of complexity. So big O n cube. So we will choose the maximum of big O n plus big O n, comma big O n square, comma big O n cube. So the
So
final
it means
complexity.
we don't add the first and second one. We only
No, no,
consider
no.
the third one, the maximum
Yes,
one.
yes, maximum one. If we are performing the sequentially.
Okay.
Okay, we are performing operations sequentially after finishing. So we will choose the maximum part, which perform the maximum times for the complexity. Okay, so this will be the complexity for this n. But in the recursive solution, you have to create this recurrence relation for code. So for example, this factorial code. So here we are calling every time. So we are starting from the n, but every time we are calling this factorial again on n-1 elements. So what will be the recurrence relation for that? So every time we are performing one constant step, so we can assume that these 3 steps are constant steps for every time. After that, we are calling same function on n-1 element. So we are starting from tn. So here t is the factorial, we can consider that. So we are starting from tn, and we are calling the same function on n-1 element, and each time we are performing big O one order complexity. So these 3 steps we are considering that this is the what is the complexity of 3 step big O1. So every time we are performing one constant steps, or we are calling the factorial part on remaining n-1 element. So these 1 plus 1 plus 1, we will perform n times. So for this recursive solution, the complexity is big O n.
So it is also same for when we are like calling the function twice.
If you are calling the function twice, no, so it become a 2 to the power n.
2
like
to the
that.
power n.
It depends on how many numbers you are calling. If you are calling 2 times, so it become a tree type things.
Tree type, yes sir. Tree type.
Yeah. So same for the merge sort. Merge sort, we are calling left part and right part.
Sir, could you please explain recursion relations complexity again?
For factorial?
Yes.
Yeah. Okay. So wait.
Sir, again we in tn minus 1 we put again here tn minus 1 minus 1. If here in place of tn,
No,
if we put n minus
actually
1.
Before calling recursively, we are performing these 3 steps. These 3 steps. Okay.
Yes.
These are fixed for every value of n. If n value is equal to 10, then this first step will be executed. If this condition is not true, then second will be executed. Okay. So for any value of n, this first we will check this condition. If it is true, then this. Otherwise, we will move to this third condition. So this is the fixed number of steps for every time. So we are considering that this 3 step as a one step, one constant step for the every time recursive call. So we will reach into 1 in n times, because we are reducing 1 every times. If we are starting from 10, so we will call factorial 9, then we will call factorial 8. So we will reach in 10 steps to the base condition, where this recursive solution will stopped. So every time we are performing constant number of steps, so we are calling recursively n times this functions. So 1 plus 1 plus 1 plus n times. There are total number of value is n. If we are adding 1 n times, so what are the value is n for this solution.
What happened to Tn minus 1?
So this is the another problem actually. Oh, you are not. So for example, we are performing T10. Okay. So every
Yes.
time we are calling T9 and one, this is the one step. We are constant step, another remaining we are performing with this T and recursive call. Once
Yes.
again, this T8 and this one. Okay. T7, then this one. T6, then one. T5, then one. Like that. T1. At this time, it will terminate. Okay, so T2, for example, T2, and this T1 and this 1, and then T0. So what is the last condition? N equal to 0. So when n become 0, T0. Okay, so okay, just yeah. So yeah, T0 and 1. Now this step will be terminated here. 1. Okay, got it. This factorial function will be executed like this. So what are the
Yes.
complexity of that? Here we are the one step, every level we are performing one step like this till last. So if we are adding these all steps, so this will be 1 into n. So here n equal to 10. So here equal to 10 steps.
Okay, thank you, sir.
Okay. Same for the merge sort. So what are the merge sort complexity calculate? How we can calculate the merge sort complexity? So we start the problem with the T n, and each time we divide this T n by 2, T n by 2, like that. T n by 4, T n by 4. See. Like that. Okay. In last step, T value is 1, so we will stop. So every step actually we are performing one merge operation after dividing it. If you see the merge sort algorithm, so after calling the recursively, we are performing merge operation. So merge operation takes n times. So this for this Tn, it will take n times. So for merge for this will take n by 2. This will take n by 2. Then n by 2 plus n by 2 equal to n times. Same for this n by 4 plus n by 4 plus n by 4 plus n by 4 n times. So till we will reach till T1 in log n time, log n steps. So this is 0, this is 1, 2, log n steps. We will reach at T1. So there is value 1 n dot 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 last again. So total number of levels are log n, and each level at each level there are n steps. So total number of steps is n into log n steps. This is the complexity for merge sort. Okay. So you can see the complexity just by looking the code. If code is not recursive, then just check the loops, how you loops you are performing, and the how loops are or depending on your inputs, just calculate the complexity according to that. If one loop is performing, that means, and loop is performing for your input completely, so the complexity will be order of n. Then if you are performing nested loop, then order of n square. So it depends on the basically loop, while loop, for loop, these things. Any other query?
No,
No,
sir.
sir.
Thank you.
Thank you, sir.
Okay. Okay, then if there is no query, then okay, bye.